then K0. All right, and then if you can now go to the to write down the predictor for this. In the GP limit, the predictor will be f of x, again the usual thing which we are familiar with. It will be the same. It will be this GP kernel, okay, and it will be again the vector of the GP kernel with one parameter x transpose times k GP inverse L. The same story times y and again the variance. The same story as previously, except that we put these kernels here, okay? And as you see, in this limit, of course, there is no n dropped out, so nothing depends on n, but it depends on the gating. So the GP kernel knows about the gating, okay? Good. Okay, so that's simple, but we want to go beyond it, okay? So where things change in the formalism of the statistical mechanics formalism that I want to integrate the weights. So let's do single weights. How much time I have?
Still have
what?
25 minutes?
35. So let me what? 25. So let me do the theory quick and then show. I need some time to explain the results in examples. Okay, so remember we had, let's say, single layer, single hidden layer. So I won't repeat the formalism because it will be the same story, and you will have g of t, which we will need to compute again, which is the log of the average over the exponent of minus 1 over 2n times t transpose times the kernel of one hidden neuron times t, average over the Gaussian w, I. The same as we had before. This is the kernel which depends on the single weights. But if you look at what this quantity is, what is t transpose k wi now t in this gating story, it's, let me write it explicitly, it's sum over mu and nu of t mu, t nu, there is some factors of sigma square over m and n0 for a single layer. And then there will be here g of x mu. Again, this is a vector, m-dimensional vector, so this will be transpose, g of x nu. And then there will be the w, the w1 dot x, the input x mu times w1 dot the input x nu. So this is the linear part. And this is, and again, I, one vector, okay? And this is the gating part, and these are the t's, okay? So now we want to integrate over the w's with the Gaussian measure of the w's, okay? So before having this, as I showed you, it's rank 1, it's phi dot t, okay? So it's all rank 1. So we got the log of the determinant of this guy was simply log of 1 plus something. Here it's more complicated because if you really want to write down this as a quadratic form of W in the matrix, then if you add the prior, then you get 1/2 of W1I times a matrix transpose times a matrix W1I. So you get this quadratic form in the exponent if I add the Gaussian prior on Wi. But now this matrix A, the matrix A of course is n by n because W is n dimension. Okay, but now A, I don't have to write it again. A will be this quantity multiplying the W's plus the Gaussian part. And the point is that this A is, although n by n, okay, but it has, this part has, it's not rank 1, this part, but it's rank m, where m is the number of gatings, okay? So the bottom, so this part m here, m is n by n matrix, but rank m, where m is the number of gating units. In the linear part, without gating, this was rank 1. So everything was kind of a scalar, but now it's more complicated, it's rank m. So if you do the integral, which you can still do, you get here now something more complicated, 1/2 log over the determinant. Determinant is on m by m matrices of I plus 1 over n times some quantity, let's call it h. And this h is m by m matrix, which is given by tracing this m, this matrix. Okay, now I'm using m is not good. Use a here and let's use a here. Okay, and this one is sigma square over n times sum over mu nu p mu t nu times gm of x mu gn of x nu times k0 mu nu. Okay, so the difference between this and the linear case, it's not simply to say, well, this is like the linear and the input is x times g, because the way the W effective is strung with the different learned weights W, giving you.
So John, I'm just confused. AG is m times n by m times n?
Which, I'm sorry, m by m. Sorry. M by m. Everything is m by m. M. This is a matrix of this is the m times n element, gm of x mu, gn of x nu. Okay? So previously, without the gating, this was just a number, okay, which turned out to be our scalar order parameter. But now the order parameter is the m by m matrix, right? Right? There is no way to get rid of this m by m matrix of order parameters which are in T. So eventually, so what we want to do then, when we come to the Hamiltonian, which is I T transpose Y, then we have we have this gating. So we have this n times the log of the determinant of this, right? So we write it as again as 1 over n times h, okay? But in order to unpack the t, because we want to integrate over t, this is only the exponent, we are using h as an order parameter, and then add minus h, minus the trace of h or u times h. So u is the conjugate variable for h, and then we have u times this, times sum over mu nu, t mu, t nu, gm of x mu, gn of x nu, times k0 mu nu. So now we have, I'm sorry, no, okay, sorry. Now we have here umn, n times gn x nu times k0 mu nu, right? So now this is our e to the, then there is ity, etc. Okay? So this is now our effective Hamiltonian on t, right? This is just a delta function on h, right? It transpose y, the usual stuff, then a delta function on h, so this is the u constraining h to be equal, constraining constraining H to be this quantity here, right? If you integrate over U, you get a delta function that H equal to this. Okay, but that's fine because so now we can integrate T mu T nu, right? Because it's quadratic in T nu. This is the quadratic term. This is the linear term. We can integrate. We can do everything. Okay, and we just get something which is a function of the order parameters. We take derivatives of the order parameters, the usual story. So it is richer than the linear network because now the order parameter is a matrix. Okay. And so that means that the kernel, the GP kernel now, will be renormalized by a matrix, not by a scalar. That's the bottom line. So so if you so I don't want to I don't have time to do the details, but you can see from the flavor of things so far that what we have is a renormalized kernel. So let me write down renormalized kernel, K twiddle. Twiddle is not temperature. I'm all work at 0 temperature. And the renormalized kernel is for mu nu will be 1 over m times K0 mu nu times, you see there is this guy, this is the renormalization here, okay? And you can think about it as a normalizing the gating by square root of u. So you can think about this as renormalized gating of x mu transpose times renormalized gating of x nu, where the renormalized gating G transpose G tilde of x is square root of u times G of x. Remember, G is m-dimensional vector, and this is m by m vector, m by m matrix. So the renormalization, you can think, the GP limit would be K0 times G transpose G. And what we change it is that we're renormalizing the gating units, the gating vector by this transformation. And U is the order parameter. And there is a question for the order parameter, and it's the same story as we had in the linear case, that UMN, the interpretation of this, is 1 over n times the average over all parameters of A transpose M AN. By this I mean, remember there are M readout because there are M pathways, M weights, so you take the vector AM and call the covariance of AM with AN, you get, this is the readout. Okay? Now there is the readout matrix. In the linear case, it was the A transpose A average. Now it is an M by M matrix, which is this. Okay, so it has it has a similarity to the renormalization in the linear case, but it is considerably richer by having this matrix order parameter and this type of renormalization. And the important point here, which I want to make, is that because of this renormalization, this is not going to be a scalar. So if you look back at the mean predictor, what now we are writing is this with the renormalized kernels here, okay? And similarly for the variance, but now the mean itself is renormalized, unlike the linear networks, and unlike our approximation for the ReLU network, which I had before, because now the shape of the kernel is renormalized. So it's not only the amplitude, but it is the kernel shape renormalization. And that has a very, I would say, profound effect on the result. Okay. Okay, and this is what I think also makes it much closer to ReLU networks or to other nonlinear networks, in the sense that if you look in those cases, in general, except for some narrow regime, you see that the predictor, the mean predictor, not only the variant, depends on n and so on and so forth. So this is much closer to to nonlinear networks. Okay, so, yes?
Do you have any simple case where we can understand what kind of U do we get? Like, for instance, is there a limit where we get a diagonal U as a solution of it? Because I expect you'll have a fixed point equation for U, right?
Yeah, yes, I didn't write it, but we have a fixed point equation of U, of course, that's what we calculate. Unfortunately, we worked hard for an approximation like a diagonal U and so on. Well, there might be cases where it works, but in general, not. And moreover, if you go to deeper network, you get a hierarchy of order parameters, matrices, m squared by m squared, and so on and so forth. So it's a hierarchical story. But I cannot. Well, we haven't found a nice regime in general. There are some cases, but it's not. No. Okay. Anyway, so that's okay. So I want to switch to, with the help of, to switch to show you result, because that's where you see what some of the beauty of the story. Now what? Well, this is here. No. All right. So the first story is very briefly what, and I don't have time to discuss, what are the details of the task. It doesn't matter here. It's ReLU, noisy ReLU teacher, learned by our gating network. This just shows you the capacity issue. So if you look at for instance, in the bias as a function of m of the number of gating per neuron, or you look at the generalization error, or the variance. So look at the variance, you can see it very clearly, the variance of the predictor, that for low m, for the parameter here, everything is fixed, p is fixed and 0 is fixed, L changes. So you see that the variance is 0 because there is a unique solution. This is the under-parameterized regime, and then the variance grows. So this is, and you see that as L increases, the capacity increases. You can go to a larger m, as shown in this formula. And the generalization error showed the double descent, and again, as a function of L, the interpolation threshold moves to the right. The bias, again, diverges and moves to the right. So this is just checking the sanity of this formula. These lines here are precisely predicted by this formula. Okay, so here we did the following thing. So let me explain. So the ReLU network, the teacher is a ReLU network, and and here are the input. The input are segregated into sections, like five sections. In one case, the W of the teacher is fully connected. In another case, W of the teacher is more heavily attending to one part of the input. So it's connected to all of them, but those connections are stronger than those, okay? So we call it preferred input. This is homogeneous input, homogeneous task. This is a task with preferred input. So this is the two cases of the teacher network. Now for the student network, we used gating, where the gating units are random. The V of the gating units are random, but they have localized receptive fields. So each set of G's look at that part of the input, okay? But they have the same strength. So we are just random V and for the gating, but each gating is looking at a subset of the input, okay? And then the question was, after learning, will the system discover, in this case, hey, but these are the important input, not this one. Now, the gating don't know about this because the gating are uniformly distributed, allocated to all the inputs, okay? So only the Y's can do that. So the question is, learning of Y learning of the W will use the localization of the gating to discover the fact that in this case, this is the important part. Okay, so that's the idea. This is why we chose this thing. And here's what you see. So in homogeneous case, for these parameters, this is the theory. So the generalization, this is the bias, this is the variance. The variance is negligible for these parameters. This is the bias. So first of all, you see here what I said, that the bias of the predictor strongly depends on n. In this regime, the variance is negligible compared to the bias, and the generalization error goes down with n. So here the GP limit is better. You expand the network in these parameters and you get better performance. What I'm showing here, this is the theory, and this is the same gating network, but doing the naive graded descent without any exploration, but starting with the same sigma as here. So you can see that qualitatively the same behavior, because we discussed it last week. So this is what I mean, graded descent versus theory. It's the same linear gating network, here just using the naive graded descent, and here we're using the posterior, the statistical mechanics approach.
So sorry.
Yes.
To understand a bit better.
Yeah.
Here the gating is like 1 or 0, selecting sections.
Right, they are like perceptron like 1 of 0, but whether they are 0 or 1 depends on v dot x, but here they are localized, v, okay, right. Okay, but you see, here is the preferred case. In the preferred case, actually the error goes up with n, okay? And the reason for that turns out to be that for small n, the network is narrow, and the W learn the fact that there is a preferred input. So you can see n equals 20. What I'm showing here is the H, the renormalization matrix. And you see that the renormalization matrix is the element of the normalization matrix is strong for the first 10 by 10 block. These are the block of gate. The first 10 gating happen to be those that are attending to the preferred input, and the other one are to the other parts of the input. And again, the gating themselves are uniformly in terms of their strength. But the W learned the fact, and this is done by, this is reflected by having a renormalization matrix heavily centered here. But as you go to larger n, basically, to your question, basically you see that H is basically diagonal identity. You asked it, or, yeah. So in the large n, you go back to the GP limit. Okay, so the renormalization matrix is that diagonal. Okay, and you can see here the ratio between the strengths of these elements to the rest goes down with n. So in this case, this is I think a nice example where a narrow network is helping because by the fact that the network is narrow, it forces the W to attend to the gating units which are the relevant one for the task, and this is reflected in the structure of the renormalization matrix. So this is the behavior, but you can see here what the renormalization does. In this case, what the renormalization does is renormalize the kernels to have a bigger strength. The renormalized gatings are stronger here than here, although the unrenormalized gatings are the same. Okay? So that's the effect of gating renormalization. I think this is a nice example. And this is, so we ask, okay, what happens if we just do student ReLU on the same task? Okay, just ReLU network for the student, no gating. And indeed, you see that the ReLU network is the same story. If the number of if the width of the ReLU the student network ReLU for the same preferred task, if it's narrow, this is the strength of the weights projected from the first part, from the preferred input. And this is the, and so on. So you see that the most of the weights, the strength of the weight are focused on the preferred input. But this is for relatively small n, but for large n, this is faded. So all the weights have the same strength, like the GP case, okay? So my take-home message, one of them is that the linear gating is nice from various aspects, but it also nice you can do the theory and you can get predictions which are qualitatively at least are performances which are, or features of performance which are obeyed by standard ReLU networks. And you can see here that in this case, the ReLU network also, the generalization error increases with n for this reason, because you're overfitting, you're not attending to the right input. Okay, so sigma, it's interesting, the regularization parameter sigma. In the linear case, it's always the case that sigma goes to 0 is the best, okay, in terms of generalization. But this is not the case here. So this is an example of MNIST, and there are many parameters here, but it doesn't matter. I want to focus on this. The error rate, again, the theory, and I'm sorry, the theory or the graded descent optimization of this linear gating. Now you see that there is, as a function of sigma, depending on the parameters, but for some parameters, there's optimal sigma. And again, this is again a feature of nonlinear networks in general, not only gating, that depending on the task, you will have an optimal regularizer for the generalization error. And this is the case. And remember, the variance is always best for, always 0 for sigma goes to 0. So in terms of the variance, it's always better to be small sigma equal to 0. But because in the nonlinear case, sorry, the mean, the bias also depends on sigma. You can see it increase. So if you want to balance the increase in the bias and the decrease in the variance, you get an optimal sigma. Okay, so this is again a feature which is shared by these linear gating networks and ReLU on other networks. Okay, how to choose the gating? Okay, so here is a task. It's again MNIST task. I'm showing you here 3 curves. Okay, this is as a function of the number of gatings. So the dashed line is the ReLU. If you take, so this is just MNIST classification of 0 and 1, and you can use, let's say, a single layer ReLU, and you get, it, of course, independent of M, and you get this baseline of generalization error. So now we ask, what happened to our gating network as a function of M? Will it approximate the ReLU performance? So we have 2 choices. One is random gating, where this V is just random. This is this curve. And the other one is pre-trained. By pre-trained, I mean it's unsupervised. You take only the input, you cluster them, and then you put you put the V there to be one of the cluster centers. So so it's like the gating is like doing clustering of the input, and you can see both of them seem to converge for large M to ReLU. So I'm not saying this is a theoretical statement. I would like to prove it, but this is an example where for large M it converges to the ReLU behavior performance, but the convergence is much faster in the pre-trained versus random. So choosing cleverly the gating does pay off. Okay, what about depth? Again, interesting stuff. So for the gating one, for the GP gating, you can show that for any M, so what I'm showing here is the shape of the shape of the kernel. So you can write the kernel as a function of the angle between x and between 2 vectors, x and x prime. I renormalize the amplitude, only the cosine angle between them. And for this model, you can show that the different curves are different L. So you can show that as L goes to infinity, it becomes a delta function except at 0. So it's completely flattened the kernel. This is for the GP kernel. Now for the renormalized kernel, it does this, but in much slower rate in terms of L. So here's the example. So here's the histogram of the kernel, the non-diagonal, the kernel elements. Again, the normalized kernel element. There is no amplitude here, and this is for the GP limit, where you can see that very quickly it goes to everything is concentrated around 0. And here you see that this is not the case, that eventually it will do it, but it's very slow. So even for L equals 4, where here it's almost everything is here there is a broad range of angles in the kernel. So the take-home message here that renormalizing the kernel, meaning working in a narrow network, slows down the rate of flattening of the kernel as a function of depth. Okay, so in this case you can see that the error and also the bias in this particular case you get an optimal. This is just an example. You get an optimal performance at L equals 2, both in the GP and in the renormalized kernel. However, there's somewhat better performance in the renormalized kernel. But the point here is not the performance is really depends on the task, but this is the generic behavior, that the renormalization slows down the degeneracy of the kernel as a function of depth. Okay, and finally I want to show the result of multiple tasks. So multiple tasks here is the example. The example is that, okay, first of all, what does it mean multiple tasks? So there are two tasks, the same data. We take mnist digit 0 and mnist digit 1, permuted multiple times. Okay? In one task, the task of the network is to distinguish between 0 and 1, independent of permutation. In the other task, the system has to distinguish between permuted and unpermuted, independent of the digit. So they are conflicting in the labels. For the same input, they may get different labels. So, of course, without gating, you will not be able to do it. So the idea is that now here the gating are the usual gating. They get some random or pre-trained input from the real input. But in addition, they are task dependent. So for each task, some subset of the gatings are forbidden and some sense are permitted. Okay. So and it's randomly chosen. So there is some overlap. It's not completely doesn't separate the network into a subnetwork of task 1 and subnetwork of task 2, because the choice of which gating will be permitted to be open in a task is randomly chosen. So there is some overlap. Okay. So this is task 1. This is task 2, and the point is now. What we are looking now here is the kernel. So this is now effectively in this case there are double the input. You have input for task 1 and input for task 2. So for each one of them, P is 600 and now it's 1200. And what you see here, let's look. This is the theory. You can see here that that for large n, look here, for large n, n larger, the kernel, the renormalized kernel, has substantial overlap across tasks. You see, this block is the kernel within a task. And these blocks are the overlap between the kernel elements at two different tasks. And you see there is substantial overlap between the tasks. But if the network is narrow, there is hardly any overlap between tasks. So the idea is here that you can use this gating, and again, because the W are tuned to the gating, the W use it in a more efficiently when the network is narrow. So W are forced to do a significant learning, whereas if the network is large, the W is widely distributed, and there is no benefit. And you can see it in the generalization error. Again, as a function of n, it increases. So again, the message is that if you hear, it's always good to be over-parameterized. If you have regularizer, it's not true. Here the regularizer is the same in both in all the cases that I'm showing, but the task is different. Here there is overfitting because when the network is narrow, there is a more pressure on W to separate the two networks effectively from the two tasks, where the network is large, the network can solve the problem without doing it, and therefore it overfits, and the generalization error increases with n. So I think this is basically a sample of what I wanted to show in terms of the results. there are many more things that you can of course apply it to, and more deeper layers and so on. But but I want to conclude these 3 lectures showing you where I think is the frontier well, I don't want to say frontier is a big word, but what we can do with the statistical mechanics approximation of deep learning in equilibrium setting. So we simplify things, we don't have dynamics, we just have equilibrium, posterior distribution, and we use this thermodynamic limit. It would be nice to solve by full force the full nonlinear deep networks. I think this is harder. It would be nice to do it, but I'm not sure. All the problems, all the models that I showed, either approximately or rigorously, are using the notion that we can still work with kernels. The mean predictor is determined by the kernel, the variance is determined by the kernel, the effective Hamiltonians are all determined by a kernel. And the question is, what is the kernel? Is it normalized, in what way, and so on. But it might be the case that for fully nonlinear networks, kernel is not enough. You need to really construct a theory where you have 4-point correlation of inputs and so on and so forth. And there is hints on that when you do perturbation theory. That's what you find. And this is much harder. So we are going to switch in the next, the last 2 lectures to the topic of representation in deep networks and the relation to that to neuroscience. Thank you.